hope. What questions do you have? Things going all right? Yeah. All right. Let's continue on with talking about our solving higher order linear differential equations. Right now, we're just doing homogeneous linear equations, and we have constant coefficients. We will keep that theme pretty much today. Might get to something new later on, but right now we'll just keep that theme of we'll do constant coefficients. We will change over to non-homogeneous equations today, but we'll be using those same principles that we talked about before the exam, where we'll solve the homogeneous system and then find a particular solution for the non-homogeneous part and then add the two together. That'll be the method that we're trying to use. All right, so last time we did several problems, but we didn't do any with initial conditions. So let's do a couple of those before we go on to the non-homogeneous ones. So this is number 36. Number 36 has the equation y double prime minus 2y prime plus y equals 0. They tell you that y of 0 equals 5 and y prime of 0 equals 10. So again, here we have an initial value problem. We know it's an initial value problem versus a boundary value problem because we are given information about the function and its first derivative at the same point. So initial value problem, we never change the x value or the independent variable value that we're plugging in. We would plug the exact same value into the function, the first derivative, the second derivative, the third derivative, all the way up to the n minus first derivative for an nth order equation. And that's what makes it an IVP versus a BVP. Initial value versus boundary value. We'll do it in boundary value problem in a minute, but let's go ahead and do this one. What do we do first? Yeah, characteristic equation. What is the characteristic equation in this case?
X squared minus 2.
Good. Equals 0, right? Okay. It's going to be step one in a lot of these problems. Actually, it's going to be step one in all of these problems. How's that factor? Good. All right, so in this case, we get a solution of m equals 1. We have a double root in this case, which we have to handle slightly differently. Because remember, where did the m come from? What did we use to generate this characteristic equation? What did we assume that the form of the solution was? Yeah, e to the mx, right? The m is that coefficient up in the x. We need two linearly independent solutions for this differential equation. The m only gives us one of them, so we have to form the other one. So in this case, one of them is going to be C1, and what's the first one going to be? What's our first linearly independent solution going to be? E to the x, good. The second one, typically, we would plug the second root in, right? But we can't do that here because there isn't a second distinct one. So what do we do instead? C2, good, x, e to the x. Fantastic. Exactly right. Good. Just trying to remind us what we did last time. And if it were a triple root, you'd add another e to the x, but multiply by an x squared, right? If you had a root with multiplicity 4, you'd add another one with an x cubed on it, and so on up the line. This is where basically we stopped all the problems last time, right? Because we didn't have initial conditions. So now with our initial conditions, what do we need to do? Yeah, plug it in, right? So we need to plug 0 into the function, or we're supposed to get 5 out. We need to put 0 into the derivative, and we're supposed to get 10 out. Right? Okay. So let's go ahead and take the derivative while we're here. And then we'll go ahead and plug the values in to get our system of equations. What is the derivative of y in this case?
C1 plus C2 plus C2.
Good. Don't forget to do your product rule on that second term, right? So now let's plug in our values. What equation do you get when you use the first initial condition, the y of 0 equals 5? What equation do you get?
C1 plus C2. No, just get C1.
Good. Yeah, equals what? 5. Good. So you'll get, we're going to put 5 in for the y. Let's go ahead and just plug it all in. We'll get C1 e to the 0, and then C2 times 0 e to the 0. Well, we'll get a 0 in that second case, right? So we just get C1. Oh, that was really ugly looking. We'll just get C1 here. I made that equation really easy. What do you get for the second equation?
C1 plus C2.
Good. Get 10 for the y prime. When I put 0 in for x here, we'll just get C1. When I put 0 in for x here, we'll get C2. When we put 0 in x for 0 into x here, we'll get 0. Well, since C1 is 5, we know that this one tells us that C2 is also 5. And so your final solution then will just be y equals 5 e to the x plus 5x e to the x. Questions on this one? Make sense? I mean, it's literally just what we've already been doing with finding constants before, right? There's not anything new. Let's do one more with a boundary value condition. And then we'll go on to non-homogeneous equations. So this is number 42. Number 42 has y double prime minus 2y prime plus 2y equals 0. Your boundary values are y of 0 equals 1 and y of pi equals 1. Remember, boundary values are going to be involving two different inputs here. If it's a higher order differential equation, it needs to be at least two different ones. But for a second order, it has to be two different ones. Also remember that if it's a boundary value problem, it doesn't have to be the original. Typically, it's stated in terms of the original problem, original function. But it could also be, I could have had y of 0 and y prime of pi. Or vice versa. I could have had y prime of 0 and y of pi. Or I could have had them both primes. So you got a lot more flexibility in the boundary value problems. Initial value problems has to be original function, first derivative, second derivative, all the way to the n minus first derivative. Boundary problems, you got a lot of mixing and matching you can do. Okay. That's really why they're more complicated. All right. Again, what's your characteristic equation here?
M squared minus 2m plus.
M squared minus 2m plus 2? Yeah, that's fine. Does this factor? No. So we have to use instead? Yeah, quadratic formula. I think we had one that looked like this last time anyway. What do we get when we apply the quadratic formula? Okay, cool. He already went through it. Good. We'll have, this keeps jumping stuff up on the screen. 2 plus or minus square root of 4 minus 8 all over 2. You know, the b squared, which is 4, and then the 4ac, which is 8. So you get a negative root 4 under the radical. Square root of negative 4 is 2i, and then 2's will cancel, so like Trey says, you get 1 plus or minus I. So what does your solution look like without worrying about the boundary value problems? Okay, careful a little bit though. Right when we split it up using the so we had a real part, so this was the alpha. We have an imaginary part, that's the beta. Both of them will be 1 in this case. Where does the real part go?
Oh, it's the exponential.
Is the exponential. That part's going to the exponential, right? So this will be e to the x. And then what do we multiply the e to the x by? Oh, actually, it's both. It's one and then the other, right? So it's a cosine of x in this case. The beta is your coefficient that goes in here. Which in this case is just a 1. And then the other one looks almost identical, except that you use sine instead of cosine. All right, so remember again, when your roots look like alpha plus or minus beta I, then your solution looks like C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. So far, so good? All right. Do we need, given what we're trying to find now, we're trying to find the C1 and the C2, but given the conditions we have, do we need to take any derivatives this time? No, we just need to plug them in and see what system of equations we get, right? What equation do you get for the first boundary condition? Okay, so yeah, you get a 1 over on this side. Just to plug in all the values, we would have C1 e to the 0 cosine of 0, theta, 0, plus C2 e to the 0 sine of 0, right? But sine of 0 is 0, cosine of 0 is 1, e to the 0 is 1, so we really do just get C1 there, right? What's the second equation tell you? Okay, so good. You have, yeah, you'd have a 1 on the left-hand side, right? Then you'd have a C1 e to the pi cosine of pi plus a C2 e to the pi sine of pi. Good. What's sine of pi equal to? 0. Cosine of pi is -1. So this equation would be, you'd have a negative C1 e to the pi, right? Are you going to get the same answer? No. This tells you that C1 equals -1 over e to the pi. But what did we just say C1 was supposed to be from the first equation? 1. So what do you say then? False is a good answer. Yeah, we don't get any solution, right? There is no solution in this case, right? Okay, so there's no solution to the boundary value problem. And remember, that was the difference between initial value problems and boundary value problems, right? Given a nice setup, which we have here, because we have constant coefficients, we have nice setup. It doesn't get any better than that, right? Given a nice setup, and by nice, we just have some continuity conditions that we need to worry about. Given a nice setup, initial value problems have what in terms of solutions? How many? 1. Exactly 1, right? It's a unique solution for an initial value problem. Given a nice equation to start with, right? And usually, if the equation's nice enough, then it'll be unique on some interval around your initial condition. Okay? If you hit a discontinuity, then it may not be unique anymore, but nice conditions imply unique solutions to initial value problems. But here, we have nice conditions for our original equation, and nothing funky about boundary values, right? But we had no solution. Okay? Remember, for boundary value problems, you might get no solution, you might get a unique solution, you might get infinitely many. Which sounds like a linear algebra problem, doesn't it? You might get no solution, one solution, or many solutions, right? For linear systems. So, same idea here. So, again, moral of the story, initial value problems, as long as your equation you're starting with is a nice equation, you'll get a unique solution in some interval around it, in some interval containing your initial value point, your initial point for your x. There's no such guarantee for boundary value problems. Anything can go wrong. Yes.
What's the difference between initial value and boundary?
So, how many inputs did you see in there for the function?
2.
2. Initial value probably only need 1.
Oh, that's the only
Yeah. Notice that in this case I've got different inputs, so that means that I'm not going to encompass everything from original function to the n minus first derivative. Initial value problem, you have to go from what happens at what happens to the function, what happens to the first derivative, what happens to the second derivative, all the way down to the same point. This I don't have any information about the derivative, the way I have it set up. I can do original function for one and derivative for the other, but then I've got mixed match points, so I don't know what the function does at one of them, I don't know what the derivative does at the other, necessarily. And so that's why I can throw things off. Yeah. That's the difference. Yeah, when you have a boundary value problem, you'll have at least 2 different inputs. You might have more, depending on what the order of your equation is. But you have to have at least 2. And that's what can throw things off. It's kind of like building a bridge. If you're working from both sides to the middle, you might be off when you get to the middle, right? Okay. All right. Other questions about that stuff at all? Before we do the non-homogeneous parts? All right. So actually, the next 2 sections deal with how do you solve non-homogeneous equations just from 2 different perspectives, but the 2 perspectives are equivalent. So we're only going to do the first section and not the second, because there's not any difference between the 2, practically. Okay. All right. So we're going to do 4.4. I'm going to call it, this is not the title your book gives it, I'm just going to call it the method of undetermined coefficients. And it'd be helpful if I just spell coefficients. Pardon me. All right. Rather than going through a long-winded description of what's going on, let's just talk about what the process is. All right. So this is number 4 in section 4.4. We've got y double prime plus y prime minus 6y equals 2x. Okay. So this, we still have linear differential equation. It still has constant coefficients. The only thing that we have changed is now it's not a 0 on the right-hand side. So it's not a homogeneous differential equation. It's a non-homogeneous differential equation. Sometimes that function on the right-hand side, we call it a forcing function. Forces the problem to do something rather than just have 0, it being kind of an equilibrium state, if you will. All right. So how do we solve it? Well, we're still going to use the same principle that we talked about before the exam. And the idea is that as long as I have a general solution to the homogeneous equation and one solution to the non-homogeneous equation, we add the two together, it gives us the general solution. Right? So we're going to approach it the same way. Okay? Pardon me. So, pardon me, goodness. Let's look at this. If I had a homogeneous equation, what's our big plan of attack for solving this? Characteristic equation, right? So that's still step 1. M squared plus m minus 6 equals 0. Does that factor? Yep. What's the factor as?
M plus 3m.
Good. M plus 3, m minus 2. Good. Fantastic. Which means our solutions are good. Negative 3 and 2. Fantastic. Good. Now, if this were a homogeneous equation, what would your solution look like?
C1 either negative 3x plus C2.
Good. Notice I've labeled it y sub h. The sub h is standing for homogeneous here, making sure I keep track of which ones I have. Okay? If this were homogeneous, we'd be done. Right? That's what we just did in the last section. Okay? All right. But we're not done because we don't have it equal to 0. We have equal to 2x. So I got to figure out what a particular solution has to look like. All right? So in this case, I know my particular solution can't look like a constant times this or a constant times that because I already know that if I plug this in, I'll get 0, right? I won't get 2x. So my particular solution can't look like this, okay? Can't look exactly like this. It can't be constant times one of them or constant times the other, all right? So we need to make a good guess based on both what the homogeneous solution looks like and what the forcing function, what the thing on the right-hand side looks like, okay? Now, look at the right-hand side. It's a 2x, right? So, again, think about what you have. I need to plug something into the differential equation. I've got to take its second derivative, I've got to take its first derivative, and I have to put the original function in there. And when I add everything together, I have to get 2x at the end. So what do you think needs to be in there? What kind of function do you think needs to be in there if I need to end up with a 2x at the end? Probably, yeah, some x, right? Probably x, right? Now, to make sure that everything cancels right, we'll make make it look a little bit more general, because it may not just be something times x, it might be something times x plus a constant, and then the constants cancel out, right? Probably not going to be an x squared, though. Right? Probably not going to be an x squared, because if I have an x squared, when I start taking derivatives, I don't have x squareds anymore. The only place that you would have an x squared would be right here, and it wouldn't cancel out. It needs to go away, right? Agree? So, what we're going to say is here, based on this function, based on f of x equals 2x, we guess that our particular solution, which I'll call y sub p, looks like ax plus b. It looks like some yet to be determined linear function. I just don't know what the constants are. Hence, undetermined coefficients. I mean, I need to figure out what they are. Okay? That's where the name comes from. So far, so good? All right. We purport that this is what our particular solution should look like. Well, if that's going to be the solution, the particular solution, when I plug it in, it has to work, right? So let's plug it in. What's y if it has this form? What would be the first derivative? Okay, and what would be the second derivative? 0. Good. So now we plug it in. So you would have literally plugging it into this equation, right? We'd have 0 plus a minus 6 times ax plus b has to equal 2x. And now we're going to set up a system of equations. Ordinarily, these equations won't be horribly hard to solve. Okay? Sometimes they get a little bit nasty, but most of the time they're not. So let's just multiply things out here. This you'd have negative 6ax, and then plus a minus 6b has to equal 2x. Right? Got the x terms and the constant terms. Let's just put them together. Okay? Now, again, these have to be equal as polynomials. If they're going to be equal as polynomials, their coefficients have to match. Right? What's on the right-hand side? On the right-hand side here, what's your coefficient on the x? 2. On the left-hand side, what's your coefficient on the x? Negative 6a. So what do you need to say about those two things? Yeah, they better be equal, right? So one of your equations is negative 6a equals 2. That's one equation. Well, that one's not hard to solve, but we'll do it in a second. Now let's do the constants. This is how we get our system of equations. What's your constant on the right-hand side? 0. What's the constant on the left-hand side? Yeah, the a minus 6b, right? I'm kind of giving it to you when I'm circling it. So what's your second equation you're going to have?
A minus 6b.
Good. A minus 6b equals 0. Good. We're equating x terms, we're equating constant current terms, getting our system of equations. Okay? Now, again, like I said, a lot of times your system's not going to be that hard to solve. Looking at the first equation, what does a have to equal? Negative a third. Given that a is a negative a third, plug it into the second equation. And we get what? B is an 18th. Negative 18th, sorry. All right, so now, putting everything together, let's write down our general solution. Remember, the way we write the general solution is we take the homogeneous solution and add the particular solution. What's the homogeneous solution in this case? Good. And then we add the particular solution. What's the particular solution in this case?
Negative 1/3x.
Good. And then we're done. It is very interesting that you do a class involving differential equations and we do so much algebra and very little calculus. right? There was your sum total of calculus in the entire problem, which was not hard calculus at all, was it? Okay. Everything else is literally an algebra problem. Absolutely everything else about the equation about this problem was algebra. Okay. Ready to do another one? Since that one was so much fun. All right, let's do number 8. Number 8 has 4y double prime minus 4y prime minus 3y equals cosine of 2x. First step. Yeah, find the homogeneous solutions, right? So what's your characteristic equation in this case?
4x squared minus 4x.
Good. Is that factor? I think it does. Makes it a little bit easier when I know it has to be a 3 and a 1. Not a lot of choices I have there. So just a matter of playing around to your coefficients match. Of course, if you can't figure it out, what can you always use to solve a quadratic? Quadratic formula, right? So if you didn't see it right away, use quadratic formula and have it spit it out for you. You could always use quadratic formula. What are your two solutions here then? Good. Negative a half and 3/2, right? From that, we should now be able to write our homogeneous equation. What is it? Homogeneous solution, sorry. I said equation, I meant solution.
C to the e to the negative 1/2x plus c to the
Good. Good. Halfway home. We got half the part, we got half of what we need, right? We've got the homogeneous part, we need to do the particular solution part. Okay. So now that with the particular solution part again, we need to, well, I meant to do highlighter, not. That's what I meant to do. To highlight it, we need to look at that, right? Now remember, we need to make an educated guess, right? So the last problem, we had a 2x on the right-hand side. We said, well, I got to plug the function in, I got to take a derivative, I got to take a second derivative, and end up with 2x. It better be powers of x that I have to work with, right? And we said we didn't want an x squared, because if I take the derivatives of x squared, the powers go down, I don't want anything to cancel out with it when I have the plus y, right? Because there weren't x squareds on the right-hand side, okay? Do you think I'm going to use powers of x here when I have a cosine on the right-hand side? No, that's probably not going to work. Because if I take derivatives of powers of x, I get powers of x, right? So what function or functions do you think we might want to consider, since we know we need to end up with cosine of 2x when we're done? Yeah, sine and a cosine is probably what we need to use, right? Derivative of sine certainly gives me a cosine. Second derivative of cosine also gives me a cosine, right? So when I want to put things together here, I want to try to make the most general thing I possibly can that also makes sense, right? That was why we used the ax plus b in the previous problem. Well, I can take the derivative of a constant. That's okay. I may need that to adjust when I take the derivative of the x, but it made no sense to put an x squared in there. All right? Here, I may need a sine, I needed a cosine, but it doesn't make any sense to put an e to the 5x in it, for example. Does that make sense? Okay. So, pardon me. So in this case, given this function, we guess, it really is a guess, I mean it's an educated guess, but we guess that our y sub p has the form some constant times sine x plus some sine of 2x, and then some constant times cosine of 2x. Literally a guess. We don't know it has this form, but it probably does. And remember, we don't need every single particular solution. How many particular solutions do we have to have? One, right? We only need one particular solution. The reason I mention that is because if I take an e to the 3/2 x, for example, and add it to whatever we end up with here, that also is a particular solution. It also works. Didn't help us, but it also works, right? The reason why this method works is because we literally only need one. We don't need all of them, right? Okay? All right. So we guess that we have this. Now we have to do a little bit of calculus. Again, not horrible. First derivative is 2a cosine 2x
minus.
Good. Minus the 2b cosine 2x. And now take second derivative. Okay. Good. Just to emphasize here, we've written it correctly, but just to emphasize, A and B are not. Oh, yeah, it's cosine. You said. No, I wrote the wrong thing on the previous line. This should be cosine. Sorry, that was me. I wrote the wrong thing. And then we just went off the wrong thing. Go back to what I was saying. We don't know what A and B are, but they're not arbitrary. Okay? So we're not going to absorb the 2 and the 4 in there, like we would with an arbitrary constant when we do an integral. These constants are not arbitrary. We're trying to figure out literally what the constants are. We're trying to solve for them. Okay? So I know in other problems we've absorbed things into arbitrary constants. That's not what these are. In particular, we haven't integrated anything. Right? If you want an arbitrary constant, they're over here. Those are your arbitrary constants. Okay. Okay. Now we plug it in and see what we get, right? So I need to do a little bit of room here. I need to do 4 times the second derivative. We found our second derivative there. We need to do minus 4 times the first derivative. Make sure I don't mess this up like I did the last time. We need to do minus 3 times the original function. And when we're done, we're supposed to get cosine of 2x. Right? We could simplify all of this mess, but remember, all we're trying to do is get a system of equations for our coefficients, right? I don't need to play algebra games to make this all look super nice. I just need to figure out what my coefficients have to be. Okay? Let's work with the sign. On the right-hand side, what's your coefficient on the sign? 0, right? So whatever I give on the left-hand side, I'm going to set it equal to 0, right? Now let's look at where your coefficient is on the left-hand side. Let's look at this first thing that I wrote. What if I look at this? What's your coefficient for the sign going to be? It will be 0. Be negative 16a when I distribute it through, right? Look at this one. What's your coefficient on your sign going to be? Cosine, or sorry, on the sign. It's going to be that times that, right? Be a positive 8b. And here it'll be a minus 3a, right? So putting all the, let me just highlight them in here. I'm looking at the signs. It will be this one, and this one, right? That's what's going to give me sign. The coefficients are going to be negative 16a. Let me scroll up a little bit. Negative 16a from the first one. Plus 8b from the second one. And minus 3a from the third one. And again, what did we say that's supposed to equal? 0, because that's how many signs we have, right? I'll label it over here. Putting an apostrophe there. Those are the sine 2x's, right? Let's do the same thing for the cosine 2x's. And I know that the apostrophe doesn't really make it plural, but go with me. Okay. What should be the right-hand side of the equation? What's the coefficient on the cosine 2x on the right-hand side?
Minus 16.
Right side. Let's do the right side first, because that's the easier of them. I mean, what's the coefficient out in front of this cosine 2x? This is 1. Yeah, good. So the right-hand side should be a 1. Right? We're trying to equate the coefficients, right? The thing that's on the out in front of this cosine of x is a 1 times cosine of 2x, right? Now let's do the left-hand side. And I think you were starting to do the left-hand side for me. What are we getting on the left-hand side? Good. Negative 16b. Good. 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 Yep, exactly right. Good. I'll do that in a different color here. Here is that one, and that one, and that one. Right? Put them together. Okay. All right. So let's simplify it a little bit. Why didn't you just let me scroll? So negative 16 minus 3, I got a negative 19a plus 8b equals 0. And then we've got a minus 8a minus 19b equals 1. Yeah. Pick your favorite method for solving these things. Doesn't matter what it is. You could use elimination, but with 8 and 19, I don't feel like using elimination. Solve that for b. We would add the 19a over and divide by 8, so you get 19 over 8a. Yeah. So then plug that into the second equation. We've got a negative 8a minus 19 times, for heaven's sake, 19 times 19 over 8a equals 1. 19 times 19 is 361. Add an 8, so you get what? 369 over 8. Assuming I did my arithmetic correctly. 19 squared should be 361 and add an 8. Then I just need to multiply by the reciprocal. And then your b becomes 19 over 369. Ooh, that is ugly. Whew. Assuming I did my arithmetic right. Feels like I did it right. It would be, thank you. Yep. So then going back to putting everything back together again, because I know it's been a minute. Remember, you take your homogeneous and then add your particular, right? What was the solution to the homogeneous? Good. And now, I guess it's a minus. We put our particular in. We did a sine x plus b cosine x, right? So it'll be minus 8 over 369 sine of 2x minus 19 over 369 cosine of 2x. Are you kidding me? 2x. That okay? It's algebra. I know it's not necessarily nice algebra, but it's algebra, right? Let's do another one. Because you're probably asking, does it get more complicated? Well, yeah, but not horribly so. Pardon me. Sorry. Let's look at number 12. Number 12 has y double prime minus 16y equals 2e to the 4x. First step. Yep, characteristic equation, which is what in this case? Good. And squared minus 16 equals 0. You can probably recognize what the solutions to that have to be.
4
Yeah, 4 and negative 4. Good. So your homogeneous equation, your homogeneous solution is what? You get e to the 4x. Good. And the other one? Good. Does it matter the order I wrote those in? No. It's just whatever you're naming the first constant, whatever you're naming the second constant. Cool. So far, so good? That part doesn't seem like the hard part now, does it? I would agree with that. All right. Let's go back over to here. Here is the thing we need to look at, right? The 2e to the 4x. Based on looking at that and thinking about what happens when you take derivatives, what do you think your particular solution should be in this case? Yeah, something times e to the 4x, right? Because when I differentiate e to the 4x, I get e to the 4x back again, right? You agree? What's wrong with that? What's wrong with that guess? What am I going to get when I plug in e to the 4x? No matter what constant we still got in front. What are we guaranteed to get? What are we guaranteed to get when we put in e to the 4x? Yeah, I'm going to get 0. right? Because it's part of the homogeneous equation. Or, gee, many Christmas, homogeneous solution, right? It's a piece of the homogeneous part, right? This doesn't work since a e to the x, or a e to the 4x would be a solution to y double prime minus 16y equals 0. That seems to muck up things, doesn't it? It's not too bad, though. Let's think about back to what we just did in the previous section. Remember we looked for, we needed two linearly independent solutions, and sometimes we had a double root? What did we multiply by to help us with that situation? X. What do you think we're going to do to help us with this situation? Multiply by an x, right? Now let's think about why this works. And again, I don't want to stick an e to the 4x on here because I know that that's not going to work in my solution at all. Okay? But let's think about why this would work. If I differentiate an x e to the 4x, I got to do a product rule, right? Right? Well, if I do a product rule, I get an x e to the 4x that's going to pop back out again. So that part will cancel. Okay? All right. So let's see what we can do here. Let's do our derivatives. What's the first derivative going to be?
Four x plus
Good. And second derivative?
16 x e to the 4x plus 4a e to the 4x plus 8 or 4a.
So far, so good? Okay with this so far? All right. So again, let's just plug it in. Here's our equation back up here. We need y double prime, which is 16a x e to the 4x plus 8a e to the 4x. And then minus 16y. That's not what should have happened. Oh, that's okay. Sorry. I thought that's what shouldn't have happened, but yeah, that's what happened. That's fine. He did the y double prime minus 16 times y, and that's supposed to equal 2 e to the 4x. I said that shouldn't have happened. That's exactly what's supposed to happen, because were there any x e to the 4x's on the right-hand side? No. So these better go away, because there aren't any on the right-hand side, right? Which they do. So we're at 8a e to the 4x equals 2 e to the 4x. So what does a have to equal? 1/4, right? It's the only way to get the coefficients to match, isn't it? All right, so now we're ready to write our final solution here. Y equals, what do we put first? It doesn't matter. Actually, it doesn't matter which piece we put first. But what's the solution to the homogeneous equation? It was the C1 e to the 4x plus C2 e to the minus 4x. And then we'll add 1/4 x e to the 4th x, e to the 4x, for our particular solution. That one really wasn't too bad, right? But we used the same trick we did when we needed a second linearly independent solution. If your guess is part of the homogeneous solution multiplied by an x. If x times it's a part of your homogeneous solution, multiply by x squared. Multiply by enough powers of x to where you get out of the homogeneous equation. That's the whole trick to it. So let's see if we can do another one, but are there questions on this one? All right, let's look at 16. Y double prime minus 5y equals 2x cubed minus 4x squared minus x plus 6. Oh, this is a y prime. Sorry. It's a y double prime minus 5y prime. Characteristic equation. Good. Factor out the m. Our solutions become 0 and 5. Which means our homogeneous solution looks like what?
C1.
Okay. Plus a C2, good. So it's C2e to the 0x, right? So I got that extra constant on the end. All right. So far, so good? Now again, looking at the right-hand side of our equation we're trying to solve, what do you think a good guess would be for your y sub p? Plus a d, yeah, good. So I have a cubic function on the right-hand side. So our guess would be that I probably need some sort of an arbitrary cubic function as my particular solution, right? It's a good guess. Something I'm going to do at the end, right? Does that work in this case, though? So remember again what we said in the previous problem. This is a little harder to spot, but do I see a piece of the homogeneous solution that's also a piece of the particular solution? It's a little harder to spot this one. The previous one was easy, right? Because I had e to the 4x in those spots. This was a little harder to spot. Do you see a part of the homogeneous that's also a part of the particular that we just guessed? The constant, right? This constant is a solution to the homogeneous. So anytime I put this constant in to this equation, I would get 0 no matter what. So this plus d on the end over here doesn't add anything to my particular solution. Because if I plug the particular solution in there, that piece is always going to give me a 0. It doesn't give me anything. In particular, I don't know what d has to be. It can be anything, right? Particular solution means we're trying to find one. If I come up with it could be anything, then it's not a particular solution. It's not one, okay? But this was a little harder to spot, but it's there, right? I've got a constant here, constant here. So this is a good guess, but it's not quite right. What do we need to do to adjust it? Multiply it by an x, right? And I need to multiply the whole thing by an x. I need to take this entire particular solution, multiply it by an x, and end up with ax to the 4th plus bx cubed plus cx squared plus dx. By the way, this might make a little bit more sense to you if you were looking at it and kind of clever at the beginning, because when I put the particular solution in there, I'm taking a second derivative and a first derivative. I don't have the original function at all, right? If I started with x cubed, I was never going to get an x cubed back out of it. We were going to have to multiply by an x regardless. Okay. All right. Now let's do the relatively easy part. So let's take the derivative. It's a polynomial. Polynomials are our friends. Those are easy to differentiate, right? First derivative is what?
4ax to the third plus 3bx squared plus 2cx.
Good. And then our second derivative,
12ax squared plus 6bx plus 2c.
good. Now we're going to plug this in to the equation. So we'll have 12ax squared plus 6bx plus 2c. That's what we had for the second derivative. And then minus 5 times the first derivative, 4ax cubed plus 3bx squared plus 2cx. Maybe. Plus t. And that's supposed to equal 2x cubed minus 4x squared minus x plus 6. That part okay? Now, I could do a bunch of algebra and gather like terms and all of that stuff, but really I just need a system of equations, right? I need to equate coefficients. Let's work highest degree coefficient to lowest, because I think it'll help us out here. What is your coefficient for the x cubed on the right-hand side? Right-hand side. But you're right for the left-hand side. It's a 2, right? And then it was a minus 20a on the left. I agree with you. So when we equate x cubed terms, we get negative 20a equals 2. Right? There aren't any other x cubed terms besides that one. We agree? Which makes a easy to solve for. What does a have to be? Good. Now let's do the same thing with the x squared terms. On the right-hand side, what's your coefficient for the x squared? Good. What's your coefficient for the x squared on the left-hand side? I think it's a positive 12a, isn't it? Yeah. So it should be 12a minus 15b. We know what a is. Can we figure out what b is pretty quickly? Yeah, it's not too bad. Negative 15b equals, that would be negative 12 over 10, which is negative 6 over 5. I need to add 6 over 5 to the other side. 4 is 20 over 5, so I'd have a negative 20 plus 6, which is a negative 14 over 5. Assuming I did my arithmetic correctly. Trace has a calculator. He should be telling me what it is. Steve. Yeah. 26? Okay. Okay, so I think you subtracted instead of added. It's positive 14. We have a negative 1/10 for a, right? So I'm gonna have to add it over, and it was a negative 4.
I had the negatives.
Yeah. We should get 14 over 75. Yes, it should be positive 14 over 75. It's easy to make a little error on these. Ooh, we got 1 minute. What's the equation for the x terms? Good. Yeah, so 6b, oh, for God's sake. Glad I'm only teaching one class today. Minus 10c equals negative 1. Oh, did you get that one, Trace? Or are you correcting it?
No, correcting.
Ah, gotcha. I didn't feel like doing this one on my head. Okay, well, let's see. I would have 28 over 25. We're subtracting it over. 28 plus 25 is 53. But negative 10c equals negative 53 over 25. So your c should be 53 over 250. By assuming I did my arithmetic right. Did I? Yes. All right. Last equation should be your constants, and I'll just write it down real quick since we're out of time. We should have a 2c minus a 5d equals 6. I think I'm out of doing this out my head at this point. 53 over 125. 125 times 6 is 750? 750 minus 53 is 697. So D is negative 697 over 125 times 5 is 625. Is that right? Yay! It's a lot of arithmetic in my head. All right, so then finally we had a C1 e to the 5x plus a C2, and then we need to add in our final answer here. The A was the coefficient on the x to the 4th. The B was the coefficient on the x cubed. The C was the coefficient on the x squared. And the D was the coefficient on the x. And you would think that they would put in better numbers. I'm going to write the authors. I'm going to file a formal complaint. I'm not really going to do that. You will not have nasty numbers like that on an exam, I promise. Because that's ridiculous. that completely just obscures the point of the whole problem. All right. This okay? Does it make sense what we're doing? All right, cool. All right. Have a good weekend. Sorry to keep you a couple minutes late. Sorry to get started late. It was the whole technology issues with the stupid pen wouldn't write. But have a good one.